let me go ahead and start recording here. That will happen, for example, if you have a syntax error, or you have a loop, or you have something that isn't doing the right thing. When Swing draws that design window for you, it's actually kind of running your code on the fly. And so if something changes in your code that potentially breaks the behavior, it can actually mess up the design window. And in that case, your only option is to kind of go back through your code and try to figure out, what's wrong in there. And sometimes it'll just be a syntax error, and that's easy to find because it's, highlighted. Sometimes it can be something more subtle. It can be an uninitialized something, so that there's kind of a null pointer exception happening. And those can be a little harder to find. And sometimes Swing will just throw up, and it will say, unexpected exception, reparse, and you can hit the reparse button, and sometimes that will fix it right away. Sometimes it takes a few reparses. But if it suddenly breaks, try to be aware of what changed most recently, and see if you can change it back, and then figure out why that change broke things.
I mean, it's kind of weird because when we ran the program, it was working fine with no errors and nothing, no pointers or no pointer exceptions. But it's just the design table. It just doesn't want to show. Which kind of which means we can't really add like new things like the score and so on. So me or my other teammate might be in office hours tomorrow, but I'll have to ask him which one.
Yeah, definitely. Alright, let me see if I can reproduce this. So I don't know what this. Okay, so this was some old drawing program we had, and if you open up the source code, right, you can go to your design tab. Oh, here's another helpful tip. If something happens and you don't have this design tab anymore, you can right-click on this file and you can say Open With, and say Open with Window Builder Editor. And if that changes, right, then when you double-click it, it just shows you. No, it's still being smart enough. But if that goes away, just right-click and say Open With, and say Window Builder Editor. And that should bring back the design tab. So yeah, the design tab should show you a picture of your window. But if something goes weird in here, I don't know if I can actually break it. Right, then nope, that didn't break it. Alright, so that broke it, right? So I made a mistake in my source code, right? I changed the name of my content pane or something, and so now my button's not appearing, my drawing panel's not appearing, and so on. And it's easy to find in this case because I can look for syntax errors, but Dot's program, there's lots of opportunities to have pointers that haven't been initialized and won't get initialized until something else happens, and sometimes that will cause Window Builder to have problems. Don't show up in the design tab anymore because they only appear under conditionals. Mouse clicks events. Yeah, that makes sense. So yeah, definitely come by office. We can look at that. All right, yeah. Other questions on PA4?
Someone mentions about separating classes, but does it really matter how you design your classes in order to get the display to work or not work?
There's lots of ways to do it that will work, and lots of ways that won't work. It's definitely important to have, you know, a separate class for whatever object you're going to draw your dots on, right? So in this case, it was a content pane that was inside here, but that's almost certainly got to be its own object because you need to override the paint method. I have seen people do programs like this with, you know, just a J-frame, and it's a lot of work, and it's not a very natural feeling solution. So I would say split it into, you know, pieces that make sense for you, and probably most people will do, you know, a J-frame for the whole thing, a content pane that you always get here with Window Builder, and then another kind of J panel inside here for the actual area of dots, and then probably putting buttons on this J panel that you get inside the J frame.
Question.
Yeah, go ahead.
How would you, so you put the, you know, another J panel inside there. Would you say that that J panel would be inside a different class, or would it still be inside your main file, I guess?
So that inner J panel that I'm going to use for actually drawing the dots, I would make that, you know, a my panel, or whatever you're calling your extension of a J panel, so that you can override the paint method. And you can create that by, you know, inside here, finding a J panel and dropping it down in here, make it a little bigger than that. And then in your source code, that's called panel, just change this to be, you know, a my panel. And probably declare it up top.
Oh, and this my panel is a different class you made.
Yeah, and then my panel will be another class, so I'll go back to the beginning here and make a new class called my panel, and in the class I'll say it extends a J panel, and then override the paint method. Yeah, go ahead.
Oh, sorry, I was agreeing.
Okay, cool.
Nodding along.
Yeah.
My voice.
All right, cool. All right, let's go through the midterm and get that out of the way. So let me close this. You want to do traffic lights instead? Everyone loves the traffic light experiment. Alright, let's see. 223A. Alright, there's our midterm. So midterms were good. So a few hundreds on there, which is fantastic. A lot of 90s and 80s and high 70s. So didn't really see anything in here that alarmed me too much across the board. Other than a few cases where people you know, either didn't follow the instructions completely or missed some detail of it, or things like that, which you know, might cost a few points on an exam, but you know, in programming it's all about details, right? And hopefully, you know, when you're writing critical control software for a Mars, you know, explorer, it's not going to be something where your boss says you've only got 60 minutes, you know, and it's going to cost you 10 points for each minute you turn it in late. So hopefully you'll have more time on the job. But the attention to detail is always critical, right? And so that's kind of an unfortunate artifact of having a time limit on a test. But I can't bring myself to do take-home tests for these courses. So, but that can end up dinging you, you know, a few points here, a few points there, and you end up with a lower grade than you wanted. But conceptually, right, I feel like people were in a good place with understanding Java and classes and so on and so forth. So question 1, Java class named Velocity, 3 private integers, vx, vy, vz. Let me pull up my notes and see.
Question.
Yeah.
In Eclipse, there's this really annoying error that talks about a serial version, UID. Well, it's not really an error. It's just
Yeah, it's a warning.
And it's just, I don't know, I don't like red squiggly lines. It kind of drives me nuts.
So you can turn off warnings, and that's a good one to turn off. Right click on it and it should give you an option for muting it. And it's basically it wants you to have this serialized unique identifier for your file, so you can ignore, or you can have it generate this cool static final long hexadecimal number, and then pretend that, like, you know, you came up with that yourself or something. But yeah, ignoring warnings is good. So let's see. Let me pull up comments. All right. So question 1, couple of issues. So you wanted a pair of constructors here, right? You wanted to be able to construct from three initial values, where you specify the values for each of these privates, or where you can construct with a single initial value that's assigned to all 3 of these. So just two different signatures for your constructor. Public method named sum that returns an int, which just returns the sum of these, and that was fine for people. A reset method that sets them to 0, and a public method flip which multiplies, and those seemed fine. So other than maybe missing the constructors, didn't really see a lot of issues with this question. Question 2. So here we're doing information hiding. By taking the secret variable and making it private. So the goal was rewrite the above code to incorporate information hiding and encapsulation. In other words, do the following 3 things. Make the secret var field of some class private. So, you know, just throw private integer, private integer secret var, right? And then write setters and getters inside some class. So make a method called, you know, get secret var and a method called set secret var. And then use those inside main so that the main program still works. So up here, instead of x equals sc dot secret var, you can say integer x equals sc dot get secret var paren paren. So you call a public method, and that public method accesses the private integer. And then to set secret var, you would say sc dot set secret var parentheses 2 times x. And so it's just use an accessor here and use a mutator here. And a few minor issues, right? Some people called, you know, setter and getter without using the name of the object that they wanted to use. Some people completely neglected to change main to use the setters and getters. some people used the setters and getters in here, but neglected to write them inside some class. And so you know, issues like that. But then,
Question.
yeah.
On the one where you have to loop over on to make a like a linked list. I don't know which one it was.
Mm-hmm.
Question 3 or 4.
Question 4.
Could you scroll to that, please? I don't have it open. I did while h, and you said while h wouldn't work because it's not a boolean.
Mm-hmm.
And, so I guess how would you do that?
While h is not equal to null.
While it's not equal to null. Oh,
Yeah.
Okay. That makes more sense.
Yeah, so C, we can do this trick where we can use integers and they'll be interpreted as booleans. And null is 0, and so while h is basically saying, well, this thing is not null.
Yeah,
But
so wouldn't it work?
not in Java, that's in C.
Oh, okay.
Yeah.
Okay, so it would work in a couple of the languages I know of. But
Yeah.
obviously not Java, I guess.
And it's a pretty accepted standard practice in languages like C to do that.
Right.
But Java is a little more uptight about things like that. All right, so question 3. This method potentially generates an exception because we're dividing by something which could be 0, right? If I try to calculate, 5 and minus 5, or 5 and 0, right, my product will be 0. And this will throw an exception. So rewrite this with the smallest try-catch block possible. So, basically do everything up to here, but then right around average, say try. Average equals this. Catch, exception E. And in the catch block, you can return minus 999. If you come out of the try-catch block successfully, you can just return average. So it's really just adding, your try-catch block around this one statement. And details in there. I didn't want you to print anything if an error occurs. Wanted the try block as small as possible. Clearly, I could put a try block around all of this. That's overkill. Putting it around, these two statements, that's overkill. The smallest try block should just go around the thing that can throw the exception, which is the division. So that's what I was looking for there. And yeah, not a lot of problems there. Make sure that if you don't return in the catch block, you do return, after the try catch block. So don't lose that statement. All right, question 4. Use the scanner and string classes to write a program that reads from standard in, counts the total number of words, counts the words that are equal to ABC or quit, and then prints those counts to standard out in this form. So if your input looks like this, your output looks like that. And so yeah.
So you mark it down for not writing the main method. What do we need in main method?
You're supposed to write a program, so it should be something that you can run. So you want a public static void main that does whatever it is it's supposed to do.
What would you put in it though?
Well, so you could do class question 4 public static void main. And so what do we want to do? We want to open a scanner. So scanner sc equals new scanner. And you can open system.in. And that does not throw an exception, so that's fine. I didn't care if you wrote an import statement. Someone asked about that, and I said that's fine. But you can import the scanner class up there if you want. And then read one word at a time, so input separated by white spaces. So that was like PA2, right? So you can use has next and next. And so you can have, integer count equals 0, comma magic equals 0. and you have to do it like that. You can't just say count comma magic equals 0. That would only initialize this one. I didn't take off for that, but you have to give them values like this. And then while sc.hasNext, and so string word equals sc.next. So that's the next word, separated by white space, and now you need to do two things, right? Count the number of words that are equal to ABC or quit. That's going to be called magic, and at the end we're going to print out those counts. So we're going to, read in a word, we're going to increment our total count, and then we can say if word dot equals ABC, or word dot equals quit, increment magic, and there's the end of the while loop, and then do your print out. So print line all, what's our format here? All plus parentheses plus magic plus close parentheses. And that's the end of the main method, and that's the end of our class.
Remind me what doing the increment, like the plus plus or minus.
So that's just a shortcut for magic equals magic plus 1.
Oh, okay.
So either way, it's just a little shorter to write.
Okay.
So anything like this, right? There's different ways you can do that as two if statements, because only one of them will be true, and so on and so forth. All right, what else happened in here? So yeah, so some people got a little tangled up by reading in an entire line using next line, and then trying to analyze that character by character, look for spaces, take the stuff in between, put those into strings, and then work on those strings and so on, right? But I was actually trying to make it easier on you by having you do it a word at a time, because that's what you spent, all of PA2 doing, was using next and has next, and that automatically chunks your input into stuff separated by white space, either spaces or new lines or tabs or things like that. And if there's multiple spaces, it treats it as a single separator and so on. So that's a convenient way to pull things in, sort of one token at a time from an input stream. And you can change what constitutes a token when you construct the scanner and so on and so forth. But if you're just looking for white space separated stuff, it's a pretty easy proposition. Let's look at next. So next finds and returns the next complete token from the scanner, preceded and followed by input that matches the delimiter pattern. This method may block while waiting to input from a scan. And so your delimiter, I think you set up in your constructor. Okay. So yeah, when you construct your scanner, you can say use delimiter and specify regular patterns, regular expressions, I believe, and chunk up based on something other than white space. So it's Java's version of something like scanf, but a fair bit more powerful, but same idea. All right, and then the last question was the linked list question. So I've defined a super node. It's got an integer data field and a next field, which is also a super node. And I'm telling you that super node header is the first node of a linked list, and that if the list is empty, then header will be null. So there's no sentinel node in this implementation. It's just header is the first node if it's present. And you want a non-recursive method, integer sum, which returns the sum of all the nodes in the list, or a 0, if there's no nodes to add up. And so, what does this look like? And so here I'm just asking for the method, right? So you don't need a main program or a defining class or something. I'm just looking for a method, integer sum. Supernode H. So H is a node which is pointing to another node, which is pointing to another node, which eventually points to a last node, which points to null. Or maybe H is null to begin with, right? And each of these nodes has a data field and a pointer field. And so we've done this, a number of times, but it's always kind of the same thing, right? We want to begin with the first node, which for us is H. There's no sentinel here. And we want to iterate until we're out of nodes. And so there's, do we start with H or H dot next? Do we iterate, well, H is not null or H dot next is not null? Or or what. So this is just something that once you figure out and really kind of convince yourself of one way to do this, you can come back to it again and again and again. And if suddenly there's a sentinel node, you can do it the same way. You just seed the whole loop differently. If you want to skip the last one, you can do it the same way. You just change the termination condition. So here's the way I think of this: is while H is not null, and we're trying to calculate the sum of all the nodes, so I'm going to need a running sum, which I'll initialize to 0, and I'll just say sum plus equals H dot data, H equals H dot next, and there's our main loop. And this does the business of, okay, start here, add the data to our sum, move H over to this node. If it's not null, do the same thing, add the data, change H to this one. This will run all the way until H is this last node. We'll add the data to sum, we'll change H to be what it's pointing to, which will be null, and we'll kick out of our loop. And so now we can return sum, and there's your method. If there's nothing in the list, H will be null when we first make this call, in which case our while loop will exit immediately, will return sum, which was initialized to 0. So you don't have to special case that. And so all kinds of things that can go wrong with this, right? You might start with H equal H dot next, in which case you're skipping the first node. You might terminate your loop by saying while H dot next is not null, which would skip the last node and potentially throw a null pointer exception if H itself is null, unless you put an extra check in the beginning. If you forget to do this, then you'll loop forever. That's a really easy mistake to make. I make that every week. What else? So some people didn't actually calculate the sum of the data. They just counted the number of nodes, and that's a different question, right? So that's one issue. So while H is not valid, we talked about that a few minutes ago, this has to be something that evaluates to a Boolean. H is a supernode, so some people tried to do this as if H were a linked list, you know, an instance of the class linked list, and tried to do things like h.size or h.get and so on, right? H is a supernode, and you know, the supernode contains two fields, and that's it. There's no size method, there's no get method. If this was, you know, a uppercase L's linked list angle bracket something, right? Then we could use those methods in the linked list class. But this is a sort of handmade linked list. So you got to do the work yourself of moving down from node to node, and so on and so forth. What else did I see in there? Missing first node, missing last node. Yeah, that was about it. All right, so that was the midterm. So if you're unsure about any of this, right, and you don't want to ask now, definitely come by office hours, and let's go over it. All right, good enough.
Sounds good to me.
All right, we can take a few minutes and talk about javadoc. We did this in the B section last week, so let's run through this in here. So let's keep picking on this. So this I think was like, you know, a few weeks ago when we started playing with Swing. I made this Monday Painter project. So come down here to source default package. So we've got two main classes in here, mainframe and my panel. Let's put some documentation into my panel, right? I mean, I've got some blurbs here, but javadoc is a utility that will go through your code and look at your comments and create documentation from those comments. And so your comments can become a markup language for recording, you know, information about the code you're writing, and then javadoc will process those and create nice documentation for you. And it's pretty easy to do. So let me just go ahead and write some comments. So, you know, you can write a comment by saying /* bunch of stuff and then */ to end your comment, and you can make multi-line comments like this. But if I begin a comment block with /*, right, so 2 stars, a couple of things happen. One, Eclipse treats that differently, right, and it fills in some other lines of comments for me, including a line which says @author space and then my username on my system NIC. And so I can put information in here to describe, in this case, what the myPanel class is. So myPanel extends the JPanel class to allow drawing of rectangles, And, you know, if I just hit enter, it'll continue to fill in that star in the beginning. So my comment block looks kind of, you know, neatly organized and so on. So it provides methods for saving XY points, which are used later to draw rectangles. All right, and so author, you know, Nick. Well, I can be formal about this. I can throw my full name on there. All right. Well, that's fine. That's my comment block for my class, right? And then, you know, I've been talking for a while in our different courses about putting comment blocks in the beginning of your functions or your methods that describe, you know, what the method does, what its inputs are, what its outputs are, and so on. And I've got, you know, this one liner down here, but I'm going to do the same thing. I'm going to put a comment block that begins with a /**. And again, you know, Eclipse fills in some other fields for me, including these two lines that say @param x and @param y. It's writing these because this function that I'm about to write the code for has two arguments, x and y. So I can describe what this function does here. This is usually done in response to a mouse click. And I'm going to put a note in here that says no drawing. This is just recording the points for future use. And then my parameters, well, this is going to be kind of silly, but you know, x is the x coordinate of the point being saved. And this is the y coordinate of the point being saved. As if that wasn't obvious, right? But you know, whatever. But I might also, you know, put some notes in here. This point is saved in a linked list. Another detail, right? This will only save 25 pairs of points because we have this extra feature that if the size is bigger than 25, we're going to remove the first element. So that's worth noting in here. Only 25 points are saved, older points are removed. So now we got a big documentation block here, right? Lots of comments. Teacher looks at that, says, good commenting, right? Checks off that box. All right. And so we can do this pretty quickly. /**. Remove all entries from the linked list of points. I'm going to leave my typos in there. Overridden paint method. Traverses the linked list and draws a rectangle for each point. And I think that's all it does. All right, so here's the code that you might, you know, turn in, saying, hey, I got my comment block in the beginning of each method, and I've got, you know, a comment block in the beginning of the class, and it's got my name in it. Give me my 15 points, right? So I guess I am going to fix these. All right, so here's what you can do, right? So this utility javadoc will go through your code and it will look for comments like this that begin with a /*, and it will create HTML pages for you. And it will also pick up tags like author and param and so on and so forth. And it will use those to further mark up the pages that it creates. So I can go to project and I can say generate javadoc. And now I have a new folder in my work area called doc. And if I go down there and I look at the index, it brings up a page, and there's the documentation for class myPanel. And you can see it's an extension of the jPanel, which is a component, and so on and so forth, all the usual stuff. And there's a description of it, my words. There's the author, that's me. There's the constructor. Well, I didn't make an explicit constructor, so it just has the default constructor. And then here's the methods: do, clear, paint, and save mouseloc. And they each have, a one-line synopsis. And if I click through to them, then I can see the details, right? So save mouseloc, it's called with these things. Here's what the parameters are. Here's the detailed information, and so on and so forth. And this is, the look and feel that people who work with Java are used to dealing with. And so if you're creating, a class or a set of classes and you want to put it out there for other people to use, and your documentation looks like this, right? People will know how to work around that, how to navigate it, where to find information they're looking for, and so on and so forth. And so there's this whole markup language that lets you specify parameters, and you can specify what type of return value something has. You can mention exceptions that are occurred. You can mention things that are overridden, and all sorts of stuff, right? And it's a really simple business trying to create this. You just put your comment blocks in, start them with this special tag, and then javadoc will do the rest as far as digesting that and turning it into this this nice format. And all of this
does Eclipse have the functionality where if you hover over a function when it's used, it shows the javadoc?
Let's see.
Like if you call save mouseloc somewhere
Yeah.
else.
So if I hover over save mouseloc, it'll show me that same information.
If you call it from somewhere else, does it show it there as well?
Let's find out.
Because that'd be the only place you'd actually want it to show up.
Yep.
Yeah, that's cool.
So that's kind of cool.
This Java docs is the same as JS docs, or probably the same as all the docs.
Right. And so if I can figure out where my workspace is, home Nick Eclipse workspace. There it is. So if I come down here, I come down to Monday Painter. I'll have a new folder called doc, and if I go into there's my HTML files. And this is just, plain HTML with a style sheet. And so, if I'm putting this on a web page, I can just take this stuff and toss it into a directory, and index.html takes you to that front page, and it's easy to put this stuff on the web, and that can be useful. So that's a nice feature. I'm not requiring you to use it, but it's nice to know that it's there, and it's one of these things that if, as you're writing your code, you're doing this documentation, right? You've always got this javadoc available to you, right? And when you're working on something like dots, and you're like, oh, how do I draw a line? What was the name of that thing where I saved the line, right? Well, if you've got Java documentation for that, you can use that to help write your own code. And that's the extreme version of when I say putting comments in your code will help you while you're writing it. Well, putting comments in your code like this gives you all of this stuff while you're developing your package, and so that can be really useful. And something like PA4, we may only have a few classes, but there's a lot of interaction between them. There's a lot of methods that are going to be called. Call a method in this object from this other object, and so on and so forth. And so good documentation along the way will actually help you. Definitely a good chance to get away from the mindset of, I finished my code after, 85 hours of a marathon session. Now I'm going to add comments and turn it in, right? Well, there's a good chance that if you're commenting it well along the way, your 85-hour marathon session might be shorter. It might only be 83 hours, So it's good opportunity to play with, documenting things as you go forward, and you get the extra benefit of this beautiful, documentation here that you can like put in frames and give to people at Christmas or whatever. So that's bonus. All right, so I just wanted to mention javadoc. Like I say, I'm not going to require you to use it. I'm not going to test you on it. I might ask you, to tell me what javadoc is, but it's something good to know is out there. All right, let's take a 5-minute break, and then we're going to switch gears and start something completely new, which will be talking about threads. So we'll come back at about 5.5 minutes. All right, so I'll see you back here in a few. Well, I think the echo makes sense even if only one person is talking, because if you're hearing yourself coming back through the your own speaker, that's where the echo comes from, right?
It's not playing on my own speaker though. I think I know what the issue is. It has something to do with the Google microphone array on this laptop. I need to figure out what's going on. I've had the same issue in other programs.
Interesting. All right. Let's see.
Check out there's a really simple message dialogue thingy where you can do alerts, and then they auto close when you click OK on them.
Yeah, I found that a bit intrusive.
All right. So let's move on to a new topic. So I want to talk about threads. And threads are where things get really interesting. And you know, there's an old curse, may you live an interesting life. That's the sense in which I mean interesting. So, most of the time when we write programs, we're kind of thinking about, you know, a sequential execution of a set of steps. We're going to do this, and then this, and then this, and then this, and then we're going to do either this or that, and then we're going to go back and do it again, and so on and so forth. And that works, you know, fine for 120, 121, 224, 222, a lot of what we've done in 223. We've started to perhaps get a sense that that's not all that's going on when we're playing around with swing and we're doing graphics and we're making things appear and we're responding to events. We're perhaps starting to get the feeling that things aren't just sequential anymore. And when we talk about event-driven programming, we're changing our mindset. We're thinking about, you know, interrupts. We're thinking about things from like 270, where we hang out here in a little loop doing nothing, and then something happens, and boom, we jump over to this other location in our code and respond to that. And so there's this sense of, you know, multiple things going on at once. We may be sitting, you know, in a infinite loop waiting for events, but something else needs to know that an event has occurred and needs to respond to that and take some action. And so you know, well, I can't show you my main desktop right now, but you know, I've got a clock sitting at the top of my other display, and it's counting off seconds. And every second, the number to the right of that last colon increments. And when it gets to, you know, 59, it rolls over to 00. And that's happening regardless of what else I'm doing, right? And I'm flapping my arms around here, and this display is changing, and it's going out to you, while that thing is still counting time. And so, you know, you hop on and look at your task list, and there's 360 things happening on this machine. 4 of them are in a running state. 1 of them right now, 2 of them right now. They're actually, like, you know, doing something. And most of them are sleeping or idle in some way. And so this CPU has 4 cores. And so each core has kind of its own, you know, execution context. And so we can actually have multiple things happening at the same time on this CPU. A single CPU only does one thing at a time, right? We know this from you know, talking about computer architecture. Does one thing at a time, and it takes turns, you know, deciding who's going to get the CPU now. And so if 5 jobs want to run, there's some sort of scheduling where each job gets a little bit of time, and then the system goes on to the next job, and so on. And so this is a recurring theme in programming. As you develop solutions to different problems, sometimes there's situations where you might want more than one thing happening at once. And there's a few reasons why that could happen. It could happen for the sake of efficiency. It may be that, you know, you're trying to find a new prime number. And so you want one process that's checking, you know, this number, and another process that's checking a different number. So you can be checking 2 numbers at the same time. Or it may be that, you know, you're writing an operating system and you want to be able to respond to keyboard events, mouse events, network events, time events, exceptional conditions, you know, all simultaneously. As opposed to, you know, for the next minute I'll be listening for keyboard clicks, and then the minute after that I'll wait for mouse events, you know. So, so different motivations. And in PA5 we're going to have good motivation for using threads to make a networked version of our dots program. And so let me show you a typical example why we might want more than one threads. And this example has to do with I/O. And think about, you know, either doing fgets in C or doing, you know, scanner.hasNextLine in Java. But imagine that you're trying to respond to user input. So you want something like this. So print a message, wait n seconds, and then go back and print the message again. So I'll print the message, n's equal to 5, I'll wait 5 seconds, I'll call delay or sleep or something, you know, and I'll go back and print, and this thing just sits in a forever loop. And so a question is, you know, while this thing is running, so maybe in C I would say, you know, while 1, print hello, sleep n, and maybe up here I'll say integer n equals 5. Alright, so this is running forever. It prints a message, it sleeps 5 seconds, it goes back, it does this, that's its life. While this thing is running, what if I want to change the value of n? What if I want the user to be able to turn a knob and change, you know, how quickly these messages are coming out? So during the execution of this, I want to change n from 5 to some other value. Well, how do I do that? I can say, you know, print enter n, fgets, or, you know, has next line, or whatever, right? And set n equal to something. But where do I do this, right? If I take this and I put it up here, this will happen once. The code will ask the user for the value of n, they'll specify it, and then it'll go into this infinite loop. If I do this after the loop, it never gets executed. If I do this inside my loop is dysfunctional. Because I print out hello once, and then I ask the user to tell me how long would you like me to wait. And they type a 5. And I sleep for 5 seconds, I print hello again, and then I ask the user again, how long do you want me to wait? Well, that's not what the behavior is that I'm after. I want this thing to just sit here and keep printing a message every n seconds, but I still want to be able to ask the user, hey, do you want a new value of n? And so there's one kind of kludgy way to do this, which is to use something called a non-blocking read. And this would be a different version of fgets that would ask the question, hey, has the person typed something in? And instead of waiting until the person types something and hits enter, which is what fgets does, it would come back right away and say, nope, the person didn't type anything. Or if they had typed something, it would come back right away and say, yes, here's the thing they typed. Right? And if we have this non-blocking behavior, we can take this and put it inside the loop. And then our loop would be, you know, print the message, see if a new value of n is available, and if it is, set n equal to that. Wait n seconds, go back up to the top. But it's a slightly kludgy way to do things. It's not the only way we can do things. So this would be a classic example where what we could do is create two threads. This could be thread 1, this could be thread 2. And thread 1 just sits in a loop. Prints out a message, waits 5 seconds, or waits n seconds, goes back and does that again and again. But completely independent of that, we might have an entirely new thread whose purpose is, you know, ask the user for a new value of n, wait till they type in that new value, set n equal to that, and go back up here and ask them again. And while this thread is sitting here, you know, waiting for has next line to come back and say, hey, I've got some input available, this thread is still executing. And so this is something that pops up sometimes in PA5 where we're playing dots, we're responding to mouse clicks, but we also need to respond to information coming in from a network connection to the other player. And we don't necessarily know when that information will arrive. And so breaking things into threads may be useful there. So that's one example that'll be topical in a few weeks. There's tons of other examples, right? So you're making a video game, and you know you're moving around and you're interacting, you're shooting or whatever, and in the game you want to do checkpointing along the way. You want to save the current status of the game every few seconds in case, you know, the game abruptly ends. You don't want the user to lose their progress. Well, you probably do. But you know, you're a nice game, and so you're saving the state of the game every few seconds. Well, that might take, you know, 2 seconds to do. You don't want to, you know, every 10 seconds go into this other section of code that writes everything about the current game state onto the drive and freeze the game for 2 seconds while you're doing that. Right? That would be horrifying. So typically you would have a separate thread whose job is to snapshot the current game state and then write that snapshot out to disk. If that takes 2 seconds, if that takes 10 seconds, does not matter, right? Your main gameplay just simply needs to tell the other thread, hey, take a snapshot. And it continues, you know, responding to the user, updating the display, and so on and so forth. So there's lots of cases where being able to do more than one thing at a time is useful. And you know, the most extreme example of that is the operating system. But most of us aren't writing operating systems on a daily basis. And so there's other situations where this is useful. All right. So most languages have a mechanism to support this. In C, we looked at fork, which was a chapter 2 system call, and fork basically created a clone of the current process that executed in its own thread space, and so, or its own process space. So by calling fork, we create a second process, and then we can take that process and start doing something differently. So there's a variety of ways to do this in Java. The main way I want to talk about today is to use what's called a thread. And in C, this is a little bit painful. In Java, it's simple enough that it's actually fun. So let's let's pull up some documentation. So thread is an extension of object, but it's pretty high up in the hierarchy. And you can read all of this. It's sometimes informative, sometimes confusing. But here's a simple example. What we're going to do is we're going to create our own class that's going to extend thread. And then we're going to write a method called public void run with no argument, so it's got to have this signature. And the code of this method is the thing that we can have execute in a separate thread. All right, so let's do some sample code. All right, so I'm going to make a new class called myThread. So mt1 will be a myThread, and I'm going to make a myThread called mt2. And the constructor for a thread, I'm going to pass an integer to it so I can identify the thread. So I'm going to construct this with an argument of 1. I'm going to construct this with an argument of 2. So I'm going to call the run method inside mt1. And I'm going to call the run method inside mt2. And this is not going to do anything exciting. This is going to be a very, very uninteresting example, but we'll make it interesting a little bit after. All right, so my thread is going to be a new class that I'm going to make myself, so let's build that. And I'm going to say, well, let's just make this. Let's make a constructor. And I'll pass an integer ID. And I'm going to make a variable up here in the class called ID. And in the constructor, I'll construct with an integer, and I'll just save that in this ID variable. And I could have called this uppercase ID and said this dot ID equals ID, but I don't want to complicate things by talking about this. So this will construct a myThread object, and it will save whatever argument I pass to it in this integer up here. And my run method is just going to be a loop. All right, so we know exactly what this code is going to do, right? So my main method is going to construct two of these objects. It's going to call the run method in mt1. It's going to call the run method in mt2. When I construct, this argument is going to get saved in a variable called ID. And when I call the run method is going to print out 100 things. It's going to print out that saved ID, followed by a colon, followed by this increasing integer I, followed by a space. And at the end of that loop, it's going to say thread whatever is done. Thread 1 is done, thread 2 is done. And since I said we're going to extend the thread, I'll go ahead and put that in here. All right, and this is going to be entirely uninteresting. Right, so I called mt1.run, and it printed out, you know, the thread ID 1 followed by this integer I increasing from 0 up to 99. Said thread 1 is done, printed a new line, then it did thread 2. And if I do 3 threads, it's equally uninteresting, right? It calls mt1.run, it calls mt2.run, it calls mt3.run. So this is the expected behavior, and there's no mystery about this, right? I mean, we know Java. We know that this creates 3 objects. It saves these arguments in the ID. This runs this method, and then this method, and then this method. So far, you know, we haven't done anything to write home about. Even though I said that this thing extends a thread. Okay, so here's the magic. When we extend thread, we inherit a method called start. And all I'm going to do is down here, instead of calling run, I'm going to call start. So that's the only change. Instead of calling run, I'm going to call start. But when I do that, I get something very different. So let me clear this and run that again. Right? So thread 1 printed out its 0, and immediately after thread 3 printed a 0, and then thread 2 printed a 0. And then thread 3 did a 1, 1 did a 1, 3 did a 2, and then thread 2 came in with its 1. And clearly these 3 threads are executing simultaneously. And they're executing in no predictable order. So here we had thread 1, 3, 2, 3, 1, 3. If I run this again, we get 1, 3, 1, 3, 1, 3, 1, 3, 1. Thread 2 hasn't even started kicking in. And I don't know when thread 2 starts. We'd have to find a 2:1 somewhere. But it's certainly not in the very beginning. And if I run this again, well, thread 2 kicked in right here, right after threads 1 and 3 began.
By the way, when you do the start command, why did it just go to, why did it execute the run method inside the class?
Good question, because I didn't say run, I said start. But the run method got executed. So here's the deal. So if I make, you know, if I have an object of type thread or type, you know, something that extends thread, there's an inherited method called start. And this does 2 things. One, it creates a new thread. And then it calls the run method. So start is a 2-for-1 thing. Start is another way to call run, but before run is called, an entirely new execution thread is created. So a new thread is created, and then our call to start comes back. But that new thread goes ahead and calls run. And that's why after calling start from MT1, we immediately come back and call start from MT2, and then we immediately come back and call start from MT3. And while those things are happening, that start created a new thread, and then that new thread run was called. And so this is the result of those three run methods executing. And it's effectively unpredictable, right? For example, here thread 2 finished last. In our previous run, thread 3 finished last. In our previous run, thread 2 finished last. So this is the Wild West, right? This is independent execution contexts doing their own thing. And fairly hard to predict just by itself when things are going to happen. But what we can do is we can control when things happen by adding extra structure on top of our threads. But it's going to be on us to do that if we care about when things happen. For example, if we want to make sure that thread 2 has finished before thread 3 finishes, we need to do something to make that happen. Because if we just say, hey, start these 3 threads, you know, the fact that we're starting thread 3 last doesn't mean it's going to finish last. In fact, thread 3 could begin before thread 2, right? That's what we saw right here. Threads 1 and 3 printed out before thread 2.
I have a question.
Yeah.
It's not related to threads. Is that fine?
Sure.
So I have a class. This is for PA3.
Okay.
I have a class, and it's nested inside my main class. And in the nested class, it's got like my save button and input fields and whatnot.
Okay.
And then when I click save, I want to notify my main class that we're ready to build yield grid.
Mm-hmm.
How would I do that?
So whether it's nested inside or it's a separate class and a separate file doesn't affect it. But what you can do is does your main class construct that other class?
My main class, yeah, it does a new entry box.
So the easiest way is in the constructor, have the main class pass an argument of this. And then the constructor save that argument, and that will give it, a reference to the main class. And then you can call functions in there.
Oh, okay. Alright.
Yeah.
What would that type be, though, I guess?
Whatever type of thing the main class is.
Which is a JFrame. Okay.
Yeah, cool.
Awesome, thank you.
Yeah, you're welcome. All right, so this can be startling in a lot of ways. For example, thread 3, finished its last output right here. But thread 2 was able to get in another piece of output before thread 3 said, hey, I'm done. And, if you look at the code for this, we say, print out from 0 to 99 and then say done. Well, in between this last print statement and this print statement, thread 2 snuck in and printed something out. And one of the challenges with working with threads is we're so used to sort of thinking of code sequentially that we won't even necessarily imagine possibilities like this. Right, we're gonna see our code and say, okay, so after it prints out, I equals 99, it's gonna do this next. And you have to constantly think about the idea that unless you do something otherwise, right, at any point in time, any thread could take over execution. Now, multi-core is right, everything's running simultaneously because I've only got 3 threads. But if I did this for 100 threads, right, there'd be some sort of time sharing going on where a small set of threads would be executing and then another thread and so on and so forth. But you got to keep in mind that, like, you don't really have control over when other things might happen.
Any question?
Yeah.
So for threads, instead it runs the run method. But if you were to put more methods inside a class, like probably say like method that counts from 100 to back to 1,
Mm-hmm.
does that also get executed if you were to do mt1.start?
So
Or it,
when you say mt1.start, the only method that gets called in response to that is run. But certainly inside the run method, you could call other methods. Or independent of calling start, I could call run.initialize or run.reset, or I could call thread.initialize or thread.reset. They're plain old classes just like any other class. The only difference is they have this method called start that we haven't written here, and we have to understand when start gets called, that will make a call to run, but it'll do it in a new thread. But that's the only difference between this and any other class. So different methods, different fields work exactly the same way that we're used to.
so there is a run method inside the start class, or sorry, not the start class, the start method. I guess I'm just understanding, like, is it because you named it run? It was like overriding the run inside when you call start.
Yeah. So start. Start is a method which causes the thread to begin execution. The JVM calls the run method of this thread. And run does nothing by default, right? But we're overriding the run method and saying, hey, here's what I want run to do. And so now when I call start, right, it creates a new thread, calls run. And that's really all there is to it. I mean, if you understand that, then actually you do understand this, even though it may feel like there's something missing from that picture. That's really all there is to it. And threads get bizarre, right? So one thing is there's a lot of methods in the thread class that are deprecated. They were implemented in the earlier versions of this class, and then as things developed, people realized these are not the best way to do some of this managing of threads. It leads too easily to issues. So for example, the destroy method still exists, but it's deprecated. You'll get warnings if you use it. You'll lose credibility and points if you use it in code and so on. This was originally designed to destroy this thread without any cleanup. And you can read, why this method is deprecated. And it has to do, among other things, with something called deadlock, which is what we're going to talk about next. But so some of these methods that you'll find in here don't work anymore. They work, but they're not supported anymore. They're not supposed to be used. But mostly we're going to use the start method. And we can also use some other methods like sleep. This is a nice way to introduce a delay into a program. And sometimes we'll use join. And join is a way to wait for a thread to go away. And so if yeah, go ahead.
I just thought that that stop is
Deprecated.
Is it deprecated.
Yeah.
It's kind of interesting that stopping a thread can be not very safe for some reason.
Yeah. And the reason has to do with so starting a thread is fine, right? You're saying go, right? Once the thread is running, if you can come in from outside and stop it, or destroy it or something like that, there may be things that this thread should do when it's finished, right? So let's see if I can not get in too much trouble with an analogy, right? Starting a thread is like giving somebody a job to do at work, right? So hey, I want you to, you know, sharpen these pencils for me. Okay, so this job is off doing that, right? And it's going to take the pencil sharpener and it's going to find a quiet room. It's going to sharpen 100 pencils. It's going to put the pencil sharpener back, return the pencils to me, and say I'm done. And then it's going to exit, go home for the day, right? Now, if something happens, like it gets to be 5 o'clock, there may be something in that job which says, you know, hey, when it gets to be 5 o'clock, put the pencil sharpener back, take the pencils that have been sharpened, return those, and set a flag saying, hey, I've still got more pencils to sharpen tomorrow, right? And that works great. Okay, now if I come in and I say stop or I say destroy, that's like basically, you know, erasing this person's existence. Well, if I do that while they're holding the pencil sharpener, guess what? I can't sharpen any more pencils, right? I kicked this person out while they had the pencil sharpener in their hand, and now there's no more pencil sharpener, right? That's an example of deadlock. That's a situation where I need a resource that this other thread has, and if that thread suddenly goes away, it may not have a chance to return that resource, make it available. And now my system is stuck forever. The next time I need to sharpen a pencil, I'm never going to finish because the pencil sharpener can't be accessed because this other person who's been banished to Boogie Land has the pencil sharpener. So that's the kind of thing that happens if you can come in from outside and too heavy-handedly monkey with processes.
So basically, if you want to stop, the best way to do it probably is to have like a return statement as of like you treat it as a program, correct?
Yeah, so the way to avoid this would be to let the process itself manage when it's going to stop. And you could say something like, I'm going to have a method called, you know, stop yourself, and I'll call that method, and then inside that thread it will check for a flag that's been set from that method call and say, oh, I'm supposed to stop. Okay, so it'll return the pencil sharpener and it'll put the pencils it's got done in some place, and it'll set a status flag, and then it'll go home or exit. And so this is the whole sort of topic of dealing with threads or multiprocessing in general. The mechanics, you know, pretty simple. Extend the thread, write a run method, and then call start, right? But knowing how to use that and anticipating the things that can go wrong and so on, that's where life gets super interesting. So let's see if I can find something here. I should have dug this up before. All right. Well, let me give you an example, and I'll show you some code next time. But let's talk about this. This will be a motivating example. So unsynchronized operations. So here's an example. Suppose you have a bank. Like a money bank, not a data bank. And inside the bank is account information. And it's a small bank, so you're the only customer. So it's got, you know, your balance. And it's an integer, it's 100. So you've got $100 in the bank. And it's a small bank, but they still have ATMs because they're trying to grow. So here's an ATM. And here's another ATM. And there's connections. Alright, so what does an ATM do? It lets you deposit money, it lets you withdraw money. And the actual information about how much money you have is stored in the central location. So there's a computer here, and there's an integer called balance, and that's Nick's balance, right? And there's some sort of network connection to these other computers that are running inside these ATMs. So let's write some code. Let's write the deposit method. So I want to deposit N dollars into my account. So I'm going to use some kind of get balance method, which will read my current balance. I'm going to add N to that, and I'm going to save that as my balance. And then I'm going to have a withdrawal routine when I want to get money out of the bank. So I'm going to say get balance. I'm going to do B equals B minus N, and I'm going to set my balance. So pretty straightforward, right? Someone comes up to an ATM, they want to withdraw $10. Code runs in there, it reads the current balance, subtracts 10 from it, and then sets the balance according to that. And, you know, give the user their N dollars. And the deposit, you know, take the money from the user and then adjust the balance accordingly. All right, so this is pretty straightforward. But here's what can happen, right? So let's suppose that two events are taking place. So one, I get paid. So I've got my paycheck for the week. And let's suppose I get paid $50 a week. And two, I take out $10. Because I'm going to go to Burgerville and buy a French fry. All right, so I'm
about right.
Yeah, right. So I'm sitting at an ATM and I'm going to withdraw $10, and Clark College they wouldn't do this through an ATM, but you know, work with me. They go to an ATM to deposit my $50 paycheck. All right, no big deal. At the end of this, right, my balance should be 150 minus 10 should be 140, right? So here's what can happen. I go to withdraw my money. All right. So the first thing that happens is this program says, okay, B equals get balance. So this is going to set B equal to 100. And this step is finished. And now it's going to say, okay, let's subtract. Okay, bye. And now it says, okay, I'm going to subtract how much you're withdrawing. You're withdrawing $10, so B equals 100 minus 10. B is equal to 90. And that's done. And at that point, the president of Clark College is firing up their ATM, and they're depositing my $50 paycheck. So now this code starts to execute in this other machine. And it says B equals get balance. Well, what's the balance here in the bank? It's $100, so B equals 100. And then it says, okay, we're depositing $50, so let's add 50 to that. So now B equals 150. And, you know, the president's ATM has higher priority maybe. So it goes ahead and it says, okay, let's set the balance to this new balance B. So it changes the balance in the bank to $150. And now that step's done. All right, now we come back and my ATM is continuing its program, and it says, you know, set my balance to whatever B is. Well, B is 90, right? So it says set balance 90, and and that makes the balance 90, and it gives me my money, and that ATM is done. Well, the deposit looks like it went fine, the withdrawal looks like it went fine, but guess what? My balance in the bank is now $90. So how did that happen? What went wrong here? Let me run through it once more, a little more quickly, right? Started off with a balance of 100. This code began to run. It said, get the balance, that's 100. Let's subtract 10, that sets our B equal to 90. And now the deposit code starts running. It reads the current balance, which is 100, adds 50, which makes B 150, sets the balance to 150. That puts 150 in the bank. Now this code continues to run, and its next statement says set the balance to 90. And that puts 90 in the bank, gives me my $10. And guess what? I just lost $50.
Now it would be really nice if withdrawal went first and then the deposit.
Yeah, that would be good. So this is a classic synchronization question, right? And you know, this algorithm ran correctly. There were no errors that occurred, right? And this algorithm ran correctly. There were no errors that occurred, but something clearly went wrong. And the whole problem can be boiled down to the following. This process right here got interrupted. I read the current balance, I made an adjustment, and then I wrote the current balance back. But during those operations, something else happened. In particular, that $50 got deposited, but this algorithm had already decided what the initial balance was, and it did not take into account that $50 because it hadn't happened yet. Alright, so what's going on here? This thing right here, we call this an RMW, which means read, modify, write. And a lot of things we do in computers are read, modify, write operations. When you say I equals I plus 1, you're reading the current value of I. You're modifying that value you read, and then you're writing it back into I. So this is sort of the typical low-level behavior that's happening inside a CPU. Read something, change it, and then write it back. Read, modify, write. The problem happened in this case because this read, modify, write is not what we call atomic. The read, modify, write got broken partway through. We got to the read part. We could have done the modify before or after, it doesn't matter. But before we finished the read, modify, write, something else transpired.
Any question?
Yeah.
Or an idea. So to prevent this interruption to happen, do you have it set where if you have a certain variable equal to true, I mean like there's already a process happening?
Yes.
The second process can like wait or something.
Mm-hmm.
Even though it may sound like a obvious idea, but that's just an idea I thought of.
No, perfect, perfect.
Is that what we're heading towards right now?
Well, sort of. So let's fix this by using a flag, right? So our deposit n is going to do the following. Let's wait until in use equals false. In use is going to be a flag that we're going to set when anybody's using the balance, right? So wait till in use equals false. Well, let me do it like this. Deposit n. We'll just do a little while loop in the beginning. We'll say while in use is true, let's just sit here and spin. All right, once the bank is no longer in use, we'll set it to be true. and then we'll say b equals get balance, and b equals b plus n, and then set balance b, and then we'll clear our in use flag. And then on the withdraw side, we'll do the same thing. First, we'll check to see if in use is in use, right? See if it's true. If it is, we'll sit here and spin. Otherwise, we'll say in use equals true. B equals get bal. B equals b minus n. Set balance b, and then clear our flag. So now, right, I come along to make my withdrawal. Nobody's using the bank. I'll set that flag to be true. I'll read my balance is 100. I'll subtract 10 is 90. At this point, someone tries to deposit money. Hey, the bank's in use right now. It's going to sit here and spin at this point. I'll take my new balance of 90, write that out, clear this flag. Once I clear that flag, this will continue. Set a flag so it's got access to it, and now it's going to read the balance of 90, add the $450, it'll be 140, and then it'll clear its flag. So does this fix the problem?
I mean, I kind of want to say no for some reason.
Because you know me.
Yeah, but
Yeah.
I mean, that's assuming that, like, I think the problem is that if it's in use, you can have both browsers running at the same time. Well, probably not at the same time, but like, because you mentioned about like, well, while it's subtracting it, another thread or whatever to be used is ran, but that can happen any time, right? So
Right.
Somewhere, both of them might be inside the while loop while it's executing, correct?
So here's the problem, right? Suppose nobody's using the bank yet, so in use is clear. And suppose at the exact same instant, both of these programs start executing. And they both check to see if in use is set. And they both say, hey, in use is false. Cool, I'm going to use the bank. They both go ahead and they set in use to be true. And now they're both executing simultaneously. And we've got the exact same situation we had back here. And the problem is this is another read modify write. We're reading the in use flag, and assuming that it's false, we're going to change it to true and write that back into that flag. And since that's not an atomic operation, it's happening in separate steps, it's possible that while this is happening, this is also happening. And so they both think they have exclusive access, and they both turn this flag on at the same time. Now, if a third process came along, it would block. It would certainly find that the process was in use, the bank was in use, but these two could kick off at the same time. And so the nomenclature you might see is we need this read modify write to be atomic. So what does atomic mean, right? Atom was this idea that if you pulverize matter forever and ever and ever, it does not get finer and finer and finer. Eventually it gets down to a small indivisible particle that was called an atom. This was Greek thinking. And so the atom was the indivisible form of matter, the level to which it cannot be broken down any further. Normal instructions on a computer, when you say, repaint, well, there's a whole bunch of things that happen in response to that, and each of those things is a bunch of lines of code. When you say printf, there's a whole bunch of lines of code that execute. And those are written in C, and it's, if this, do that, and increment this, and so on and so forth. And each of those can get broken down. You can break down your program into assembly language statements. You can break those down into machine language statements. But eventually you get to a point where your statement cannot be divided any further. And so, for example, clear a file register. Put a 0 in this memory location. Might be an atomic operation, depending on your architecture. But certainly, when you're talking in C and you say something like I equals true, or I equals I plus 1, right? That's not atomic, right? That's going to be, a read the current value of I, increment it, and then write it back into I. So to deal with this problem of synchronization often needs hardware support. You need something in your hardware that you can use to do an atomic read, modify, write. And trying to get around it with software flags is usually not enough. And so in C we have things called mutexes and semaphores, and you'll get into these in a university course probably next year. And they're atomic operations supported by Linux. Different languages and different operating systems have different support for this. And so Java has ways to manage this, and the way we manage this in Java is very simple. We can just throw a keyword on called synchronized, and that will basically do this management for us. And the synchronized keyword will basically let us say, hey, I want to make sure only one thread is executing this code at a time. And it will keep track of, when a thread is executing this, and if somebody's already executing it and you say this is synchronized, it will stop your thread until it can get exclusive access of something like a flag, and then it'll go ahead and execute this code. And so we'll be able to deal with this kind of synchronization issue pretty painlessly in Java. The bigger pain point is knowing when to do this. And knowing when to do this gets into a second gotcha, which is deadlock or livelock. And so this is when you go a little overboard with trying to control exclusive access to resources. You can create a deadlock state. And so typical example of deadlock. So, I don't know, it's pencil sharpening day. So suppose you have a process that's supposed to sharpen pencils, right? And so how do you do this? Get pencil, get sharpener. Sharpen the pencil. Return the sharpener. Return the pencil. Pretty simple algorithm, right? So you're given a pencil, you have to retrieve the sharpener, you have to use the sharpener, then you return the sharpener and you return the pencil. And suppose there is a second process, and its algorithm looks like this. Get the sharpener, get the pencil, sharpen the pencil, return the pencil, return the sharpener. Alright. Hey, I've got a sharpener handy. Alright, so what happens here, right? First process comes along and it says, okay, I have to execute this code, so I'm going to get the pencil I want to sharpen, good. And next I need, so this is done. And now it needs to get the sharpener. Well, second process kicks in, and it says, okay, first step, get the sharpener. Okay, I've got the sharpener. I'm done. Now it's waiting for the pencil. This thread has the pencil. It will give up the pencil at some point when it gets to the end of this algorithm, but not until. So it's got to get through all of its steps before this thread can continue with the get pencil step. Well, guess what? This thread cannot continue until it gets the sharpener, but the sharpener is not available. This thread has the sharpener. This will give up the sharpener eventually once it gets through this whole 5-step process, but it can't get to that 5th step until it gets the pencil, which this thread has. Okay, this is a deadlock. Neither process can make progress. And this is a classic conundrum. And so we'll talk about something called the dining philosopher's problem, which explores this in more detail. But this is not a malfunction per se. Both of these processes are doing exactly what they're supposed to do. It's not like a synchronization issue where a flag, got broken up non-atomically. But the way this code is written, right, neither process can continue. And so this is called deadlock. Both processes are stuck. There's a minor variation of this called livelock. And livelock happens in real life. So how do we walk down a hallway? Walk forward. If path blocked. Change to the other side of the hall and walk forward. Right? And so what happens? You have one person walking down here executing this algorithm. You have another person walking down here executing the same algorithm. And they walk until they're right in front of each other. Well, person A, their path is blocked, so they change sides. And person B is running the same algorithm. Their path is blocked, so they change sides. And now they try to each walk forward, and they can't because their path is blocked. And so they each execute the step of their algorithm which says change sides. And now they can't walk forward because their path is blocked. And so this is what happens, when you're walking down the hall and someone's walking towards you and you start doing this dance where you're both going back and forth from side to side. It's called livelock. But it's effectively the same thing as deadlock. In this case, your algorithms haven't gotten stuck. It's not that you can't advance beyond a certain point. Your algorithm is still running. You're still moving from step to step, but the overall process is not making any forward progress. And that's another thing that can happen with processes in a system. So this is an area that's been studied, since like the 50s, I believe. And one of the people who did a lot of work on this was Dijkstra, as in Dijkstra's algorithm from 215. And the question that Dijkstra and others was studying was, if you had a machine that had, say, multiple peripherals hooked up to it. So you've got a computer, and you've got a printer, and you've got a card reader, and you've got a keyboard, and multiple processes running in here. And what happens if you have a printer that's trying to read from a card reader and send to a printer? and you have another process that's trying to read from a keyboard and from a card reader and, you know, update memory, and another process that's trying to read from the card reader and send that, you know, somewhere else in memory or store it on a hard drive or something. And you have these different threads, these different processes using different resources. And where are the situations in which you might get this deadlock sort of outcome, where this thread has the keyboard and is waiting for the card reader, and this thread has the card reader but is waiting for the printer, and this other thread has the printer but is waiting for the keyboard, right? And now you've got three processes and they're all stuck, waiting for something that a different process has. And so a thought exercise that's credited to Dijkstra is the dining philosophers problem. And so the setup is, you know, you've got 5 philosophers. And philosophers love doing two things. They love talking and they love eating. And so if you throw a dinner party for 5 philosophers, there's going to be a lot of talking and a lot of eating. So the setup is you have 5 philosophers sitting around a table. You have an infinite bowl of noodles. And you have 5 chopsticks. And you place the chopsticks in between each pair of philosophers. And the rules of the dinner party are as follows. You can eat or talk, but not at the same time. So at any given moment, this philosopher could be talking, or they could be eating noodles. Second rule, need 2 chopsticks to eat. So this philosopher might be expounding on, you know, the nature of existence, and then they get hungry and they want to eat. They need to acquire 2 chopsticks, and then they can start eating noodles. And then when they're done, they put the chopsticks down and they can continue talking. And so can only take adjacent chopsticks. And then there's all the rules that polite philosophers would follow anyway. So you're not allowed to break your chopstick. If you only have access to 1 chopstick, you can't break it in half. You're not allowed to attack the philosopher next to you to steal their chopstick, and so on and so forth. So usual nice rules of behavior. And so the question is there an algorithm these philosophers can follow that will allow them to talk and also not starve to death? And that's the basic setup for this question. And it's an analog to things that happen in multiprocessing systems. So there's a thing called starvation, which is where a process cannot get to the object that it needs, right? And so here, starvation would be, you know, for some reason you can't get a hold of both chopsticks, so you can never eat. Deadlock would be, you know, you're stuck waiting for something and you can't proceed until that something happens. So you can make some initial attempts at helping out these philosophers. So, you know, you could try something like this. If stick on the left is available, pick it up. If stick on the right is available, pick it up. So basically wait until you can pick up the stick on the left. And then wait until you can pick up the stick on the right. And then eat for 5 minutes. Return the stick on the left and return the stick on the right, and then talk for 5 minutes, and then go back up to the top. So that's one attempt to algorithmize people's behavior at this party. So first thing you're going to do when you get to the party is you're going to want to eat. So you're going to wait for the stick on the left to be available, pick it up, and then wait for the stick on the right to be available, pick it up, eat for 5 minutes, put the sticks down on the left and on the right, and then talk for 5 minutes, go back and do it again. And the first problem you encounter is that if all philosophers begin executing this algorithm at the same time, what happens? This philosopher sees, hey, there's a stick on my left, I'm going to pick that up. At the same moment, this philosopher says, yep, there's a stick on my left, I'll pick it up. And this philosopher does the same, and this one, and this one. And now all 5 philosophers have completed step 1, and they're now at step 2, which says if the stick on the right is available, pick it up, otherwise keep waiting. Well, this philosopher is waiting for this stick, which is not available, and will not be available until this philosopher returns it. Well, this philosopher is stuck on step 2 also because they're waiting for a stick on their right, and so on. And so this is a really quick path to deadlock. And so each philosopher is stuck in this state and will never leave that state because they need a resource that's not going to be released until another philosopher finishes step 4. And none of them can get to step 4 because they're all stuck at step 2. So you can start trying to embellish this. You can say, okay, if the stick's not available, put it down and wait for a random amount of time, and then pick up the stick again. But even if they're all waiting a random amount of time, it could be, since it's a random amount of time, that they all wait exactly 5.2 seconds, and then they all pick up the stick on the left again. And you've got the same situation. And it could be that every time that they do this, they just happen to randomly wait exactly the same amount of time, and you've still got a deadlock. And these are the kinds of things that come into your brain when you write code that's, got multiple threads and shared resources and so on. You'd like to assume that, if I just generate a random number, or I take your process ID and reduce it modulo 10 and say, let's wait that long, right? You'd like to assume that, this is not going to happen, but it could, right? And so how do you get out of this? So you can analyze this and you can come up with different solutions to this, and one solution is to have a waiter, right, who assigns chopsticks to philosophers. And if the waiter has global knowledge of where all the sticks are and where each philosopher is in their meal, the waiter can make, better informed decisions and say, okay, you should put down your sticks now, and you can pick up your sticks, and you can wait some more, and so on. But in a multi-processing system, if you had, a million threads running in parallel doing something useful, to have a single central controlling process responsible for all of those, that's a pretty sketchy design. Because now you have this one critical failure point that can, impair all million threads from operating. And so a lot of times we don't want centralized control. Also, if you had a billion philosophers, that waiter is going to be really slow. And so if you're making something that serves up web pages, because, you've just invented this new search algorithm, and your name is Google, right? And your way of managing your web server worked great when you had 5 people accessing your server, and now you've got 5 billion things accessing your server. Well, if you've got one waiter process that's going around deciding which process should get which page now, right, your system is dragging. So this is a thought exercise, right? And you can read about it online. There's a lot written about it. This is another thing you'll dig into more at a university. But it's an interesting way to sort of think about some of these issues around resource contention and deadlock and livelock and so on and so forth. So think about that if you like. We can talk more about it on Wednesday. Wednesday, I want to show you some coding examples that get us into trouble with unsynchronized access to shared resources, and then we'll look at how we can use the synchronized keyword to get out of that difficulty in Java. And then Wednesday we'll also talk about PA5, and PA5 will make good use of threading. And then we'll start talking about networking, which will be the other piece of PA5. So I think that's our plan for next time. All right, that's all I got. Have a great afternoon, and I will see everybody next time. All right, thanks.
Thank you. Have a good day.
You too.
That's a really dumb idea where you create like a thread of waiters, and it's sort of like a big table.
Have a thread of waiters, so that would be interesting.
I hope that's how it'll work, but I'm assuming that when you work in threads, the order of remember we talked about like order operations, where an order operation it's like order n, for example.
Mm-hmm.
I'm assuming that when you thread, that same rule can still apply when you have multiple things running at the same time.
Mm-hmm.
So, trying to think of like what algorithm would you use to serve all the waiters, or serve all the
Philosophers. Yeah, so if you can identify these, if you have philosopher 1, 2, 3, 4, 5, you can come up with rules. You could prioritize them, for example, and get out of it somewhat like that. And that's another version of having a centralized waiter, because something needs to assign them IDs. Otherwise, if you have a global ID out there, and each philosopher, when they come in, gets whatever the next ID is, well, what if two philosophers walk in at the same moment? They might both decide, I'm philosopher number 1. And then when the algorithm says, philosopher 1 should eat, well, there might be two philosophers who think that's their ID. So a lot of times we end up sort of pushing the problem around from one spot to another, but it's still there. And that happens all the time when we do this in code. We come up with a way to solve a deadlock problem, and it really just creates another issue somewhere else. So it's a lot of fun, though.
Do you have time to go over my PA4 or move on the way from?
No, let's go ahead and do Office.
Okay. Alright, I'll see you tomorrow then.
All right, cool. Have a good one.
You too.
All right, bye.